Welcome back, everybody. In this last section, we're going to talk about some applications of engineering and more precisely about finding the area between two curves through integration. So, just as a quick reminder, how do we find the area under the curve? Well, that's something that we do with the integral, and where you have to keep in mind that the integral measures the signed area under the curve. So if your function f of x, if the graph is above the x-axis, then the area between the graph and the x-axis is going to be the integral of f from, in this case, a to c1. If the graph is below the x-axis, so you see that here from c1 to c2, the graph is below the x-axis, then the integral is going to be minus the area underneath the curve. So if you want this area plus that area, then you're going to have to compute integral minus integral, where this minus sign is to compensate for the fact that your integral is negative. And then last here, we see that the graph is again above the x-axis, so the area is positive, or the integral is positive rather, and the area and the integral match each other. So in total, if we want the shaded area, this plus this plus this, we have to compute integral from a to c1 minus integral from c1 to c2, because the graph dips below the x-axis, plus integral from c1 to b. Now we're going to extend that a bit and we're going to look at the area between two curves. So here we have two graphs, f and g, and we want to find the shaded area here on the figure. How do we do that? Very easy. We are going to compute two integrals. First, we're going to compute the big area underneath the graph of f. That's something that we will do with an integral. So this will be given by integral from a to b of f of x with respect to x. And then we're going to subtract from that the area underneath the graph of g. So that's the integral from a to b of g. And we're going to take the difference of these two. And if we compute these two integrals and we subtract them from each other, we get the total area between f and g. Now you can make things a little bit easier on yourself. This isn't just two integrals to calculate, because they're both from a to b. You can write this as one single integral, a to b f of x minus g of x dx. So in practice, what you're going to do is take the difference of f minus g and integrate that from a to b. Now you have to be a bit careful, we'll come back to this later, but it's not the same. F minus g is not the same as g minus f. So if you look back at figure, you're going to have to take the graph that's the one on top, the upper graph, minus the lower graph, the one that's on the bottom, g here. So here's a small recipe for how you're going to do the computation of the area in a systematic way. If you follow this, nothing can go wrong except calculation errors. On the exam, what I often see is that people skip a step, and then sometimes it becomes a little bit more difficult. So step one is always make a figure. If you have a question like that, make a figure of the two curves that you're considering. Then two, figure out where those two curves intersect with one another. So if we make a schematic graph, so you're going to draw the graph of f of x, you're going to draw the graph of g of x, and it is this area that you're interested in. So step two says you're going to find the coordinates of the points where the two curves intersect. Call those C1 and C2. And why do you need those? Well, because in your area, you're going to compute an integral from C1 to C2. And then step three says figure out which curve is the upper one first the lower one. That is because you have to subtract the upper one from the lower one. So in this case, the upper curve is f of x, the lower curve is g of x, and that means that our integral becomes f of x minus g of x dx. And from that point on, step 4 is just integrate. Usually this is rather straightforward. These curves are never too complicated. But if you set up everything, then you know that you're integrating the right thing. So let's do a couple of examples. Please skip this one because it is quite straightforward. I'll let you do this by yourself. Let me maybe... And we'll go straight to this example right here. So we're given two curves, y equal to x squared minus 2x, y equal to 4 minus x squared. Step 1 is make a figure. And for this, to make a figure, it helps to remember that these are two curves that represent parabolas. Y is equal to x squared minus 2x is an upward facing parabola, and y is equal to 4 minus x squared is a downward facing parabola. How do I know that? Well, y equal to x squared is always a parabola. Y equal to minus x squared is a parabola. So whenever you have y equal to x squared, think parabola. If the sign of the x squared is positive, then the parabola faces upwards. If the sign of the x squared is negative, it faces downwards like this. So now making a figure. And actually, let me move that a bit. Oops. I'll make the figure over here a bit smaller so that we have enough space for the integral. So first curve, y equal to x squared minus 2x. That is a parabola that goes through, so y is equal to 0 for x is equal to 0 or x is equal to 2. So that's a parabola that passes through the origin and the point with coordinates 2, 0, and looks a little bit like this. You don't have to get the figure absolutely right. It helps to make it accurate, but if the proportions are a bit off, that's usually fine. Then secondly, we have this curve. So here, y is equal to 0 for x is equal to plus or minus 2. So this parabola is going to go also through this point and through this point right here. And it's downward facing parabola, so it looks like this. And just to add, this point has x coordinate minus 2, this is 0, this is 2. And now we can see what is the area that we have to find. It's the area that is shaded in red here. So that is step 1, making the figure. Step 2 is finding the intersections. Let's do that with some algebra. For that, x squared minus 2x has to be equal to 4 minus x squared. If we set f of x equal to g of x, so in other words, 2 times x squared minus 2x minus 4 is equal to 0. We divide by 2, x squared minus x minus 2 is equal to 0. That's a quadratic equation. You can solve that, or you can guess the solutions right away. You will find that x is equal to minus 1 or x is equal to 2. So we can also add that to our figure. This intersection point right here will have x coordinate minus 1, and this intersection point, we already found it, has x coordinate 2. 3 is determine which one is the upper curve, which one is the lower curve. That's very easy to do on the figure. The green one is the upper curve, the blue one is the lower curve. And then step 4 is write down your integral and integrate. Your area is now integral from -1 to 2 of the upper curve, so 4 minus x squared minus x squared minus 2x dx, and that is equal to, if we simplify a little bit, we get negative 2x squared plus 2x plus 4 with respect to x dx. Okay, so now we can actually integrate. We get negative x to the power 3. Oops, not divided by 3, just like that. I do make a mistake here. Negative 2x to the power 3 divided by 3 plus x squared plus 4x, and all of that between negative 1 and 2. And now if you substitute those values and you do a little bit of arithmetic, you will find your answer. Your area is 9 units. So check that yourself, but you should find that the area is 9 units. So this is a fairly straightforward problem, and it's especially straightforward if you follow the steps. Then you never have to guess or do anything outrageous. Now we'll finish off with a slightly more involved example. So here we have two curves. X is equal to 12 minus y squared, y equal to minus x. So right off the bat, there's something weird here. We have x is a function of y, not y is a function of x. So here we have x is f of y, not y is equal to f of x. Now, this kind of curve will also give you a parabola, but it will be a parabola that faces towards the left. We talked about that early on. You can have a parabola that faces up. This is if you have y is equal to x squared plus or minus some stuff. You can have a downwards facing parabola when you have minus that. You can have a left-facing parabola when x is equal to y squared and some stuff. And you can have a right-facing parabola when x is, so this should be minus, and here x is y squared plus. So here we have a parabola that faces towards the right. We can graph that, so let's do step number 1. Let's make the graph. Let's shade this in blue. So here we see that x is equal to 0 when y is equal to plus or minus square root 12. So this parabola will pass through the y-axis at points with y-coordinates square root 12, negative square root 12, and will look something like this. And if you want, you can also find the x-coordinate of this point. That will just give you the value 12. Now, secondly, the other curve, that is easy. Y is equal to minus x squared. That is a straight line with slope negative 1. The figure also tells us what the area is that we have to calculate. It's this area. But now it becomes a bit tricky, because what we see is that our usual prescription to find the area now doesn't really apply. Why not? We don't really have a function of x. We have a graph here that curves back onto itself. So it's not a function of x, it's a function of y. And if we want to do f of x minus g of x, like we were taught to do, that's not going to work here. Luckily, there's a very easy way to solve this problem, and there's actually two very easy ways to solve the problem that I'm going to show you. There's also a very difficult way. The difficult way would be to say, well, okay, I've got a little bit of area here that I can calculate by writing y as equal to 12 minus x and taking the square root. and then I'm going to add something here with a negative square root. And you can also get there, but it is a bit more complicated. What are you going to do to make this problem more easy? You're going to do an extra step. You're going to switch the roles of x and y. What does that mean? In your graph, you just flip, or you just switch x and y. You get y is equal to 12 minus x squared. X is equal to minus y. And now you make your graph again. So now we have a downwards facing parabola. A parabola that looks like this. And this parabola, oops, it's a very bad looking parabola. Let me make it just a tiny bit nicer, like so. This parabola, what do we know about it? When x is equal to 0, it passes through 12. When x is negative square root 12, it passes through the x-axis, and same for positive square root 11. What about the other curve? Well, actually, nothing has changed for this curve. You can write this as y is equal to minus x, and this is still a straight line with slope minus 1. And now, the area between the two curves is this area. And what you see is if you switch the roles of x and y, your total area has not changed. So your curves change, but the area does not change. And moreover, why do we do this? Because now we have nice functions of x, a function of x here as well, and we can continue with our usual approach. So that's what we'll do next. So step 2 is we're going to find the intersection points. We're going to find this coordinate and this coordinate, or these 2 points. How do we do that? Well, we put the 2 equations equal to one another. 12 minus x squared equal to minus x. And we solve that equation for x. X squared minus x minus 12 is equal to 0. And if you solve this equation, you will find that x is equal to minus 3 or x is equal to 4. So let's add that to our figure. X is minus 3 and here x is equal to 4. Now we have to determine which is the upper curve, which is the lower curve. The blue one is the upper curve, the green one is the lower curve. And with that, we're ready to do the easy part. The easy part is step number 4, that is the integral. So your area now becomes the integral from minus 3 to 4, upper curve, so 12 minus x squared, minus lower curve, so minus x dx. Now, that is again an easy integral. Let's simplify things just a little bit. Minus x squared plus x plus 12 dx is equal to minus x to the power 3 over 3 plus x squared over 2 plus 12x, all of that between minus 3 and plus 4. And if you substitute these values and you simplify, it's a little bit of arithmetic, you'll find the value of 343 divided by 6. Now that finishes our problem. Couple of side remarks. In the practical session, some TAs have another way of solving this problem, but it's a way that's morally speaking the same. What does the other way entail? It involves integrating along the y-axis. It's a bit hard to show on the video, but it revolves basically going back to this figure, and instead of looking at things from the x-axis like this, you look at things from the y-axis like that. And then if you look at things from the y-axis, then you're basically observing this kind of figure again. Then you don't have to explicitly switch the roles of x and y, but you're going to integrate with respect to y. Those two approaches are exactly the same, and they will give you the same answer. The last thing that I want to say is, when you do switch the roles of x and y, or when you do that change of perspective where you look from the y-axis, then it's sort of to be expected that the area does not change. Why not? Because what you're doing in either case is you are actually flipping the whole figure around the first bisector. So that gives you the second figure, and you can see that if you do that operation, then you're not really changing the area. You're changing the curves, you're flipping the curves around the first bisector like this, but that operation does not change the area. So just in case you were wondering, does the area really not change? No, and there's a good geometric reason for that. So with that, we're done with this particular example and also with section. It's very common for there to be an exam question about this, sometimes even with a little bit of a background story. But keep in mind, as long as you follow the 4 steps, then nothing can really go wrong unless, of course, you make a calculation mistake. So thank you very much for sticking with it.